concept that's fundamental to everything that we do in distributed architectures, which is everything we've been talking about so far this semester. And that's the concept of load balancing. It's a basic technology. There's nothing really fancy to it, but it's what makes all these systems work, and it makes web scale applications happen. So load balancing is a fundamental concept for us. So what is load balancing? Well, it's a way to distribute the load between several nodes in a system. Uh, and by distributing the load, what we do is we make it so that we can try and attempt to equalize the utilization of a whole bunch of back-end servers. It allows us to have multiple versions of our web tier, and because we can have multiple copies of our web servers, we can scale up, we can scale down. It builds elasticity into the system. Now, most of the time we talk about load balancing just at the front end, but you can load balance in the middle of your architecture also, and we're going to look at that also. But and then the last thing that load balancing allows you to do is to build fault tolerance into your system, where your load balancers can keep track of the status of the systems that they're balancing across. And if one of those systems fails, it can shift the load to other servers that are available to take that load. So load balancing matters to us, and it's one of those fundamental technologies for us. So the basic idea, we've got a load balancer in front of a couple of web servers, and we've got our database server in the back. This is a basic two-tier architecture, three if you count the web load balancer, and it works really well. If those web servers are just taking requests coming in from the internet, turning them into queries against the database server runs those queries, sends them back to the web servers. The web server reformats the data and pushes it out to the user. Now, there's a lot going on here because we've got that load balancer out there that needs to know, perhaps, something about the web servers behind it. Well, does it need to know? And the answer is, well, you've got all these incoming connections happening. The incoming connection is going to come from the internet to the load balancer. The load balancer is going to look at the list of machines that are available to accept incoming connections and select one of those based on some sort of algorithm to receive the incoming connection. The incoming connection then does its thing on the web server, right? But the question is, does the return traffic go back out through the load balancer? Well, it doesn't really have to. But if it did, why would you want to do that? Well, that would be a way to communicate to the load balancer the status of the devices behind it. If it didn't, then the load balancer would be receiving an incoming connection request and then just dumping it off to some server that it thinks is out there, but it really doesn't know. And that brings up the whole question of how much information does the load balancer have about the servers behind it. And that's what we're going to get at when we look at the different algorithms that we can use to determine which web server should get the next incoming connection. Oh, and by the way, we can have failover between load balancers. If we have one load balancer, what is that load balancer? Well, it's a single point of failure. And we don't want to have any of those. And so right away, you're stuck having to build two load balancers into your architecture. And then when you have two load balancers built into the architecture, everything gets more complicated because it's easy for one load balancer to know what's going on behind it. But now we've got two. Also, we've got our users connecting into our load balancer. And the question is, does the user interact with the load balancer only on the initial incoming request, or um, and knowing that most requests from our users back to our web servers are not single request transactions. Most of the time, there's a bunch of things that go on between the user and the web server that it's going to interact with. And most of the time, when you interact with a web server, it's not a single request interaction. It's a long series of requests. You request index.html, and then you receive back index.html along with a bunch of chatter back and forth of the protocols, and then you request another page. Well, does all that need to go through the load balancer each time? Or do you establish a connection through the load balancer to a web server, and then any ongoing connections are between the user and the web server? Well, it all depends. Then, what about SSL? What impact does SSL have in all this stuff? Because with SSL, you've got to authenticate that the user is interacting with the web server that represents the device, the URL that it is expecting to interact with. It gets much more complicated. So we're going to talk about load balancers as, pretty basic things. And in fact, they really are, but they can be much more complex. And when you dig into this, it gets more complicated. And it should, because it's a fundamental technology that underlines all of our abilities to scale up, to fail over, to do all kinds of things that are just the core of modern applications. So different algorithms that we could have that determine when an incoming request hits a load balancer, which web server should it send it to. You could do a static round robin so that the load balancer receives request 1 coming in, sends it out to server 1. Request 2 comes in, it forwards it to server 2. So we've got 2 web servers here. I wasn't explaining this well. We've got 2 web servers back here. And so the first connection comes in and gets sent to web server 1. Second connection comes in, the load balancer looks at it and sends it to web server 2. Third connection comes in and goes back to web server 1. Fourth to web server 2, and so on and so forth. What that does, I don't want to put this down in any way, but what that does is this really basic process that ships traffic between the 2 web servers. Well, the beauty of that is that the load balancer doesn't need to know much of anything about those web servers. It just assumes they're there, assumes that they have equal capacity to handle incoming requests, and it doesn't need to know much. So our load balancer becomes this really basic machine. Basic machines are, generally speaking, good machines, because basic means there's not as much to fail. So this is, you might look at this and say, not very sophisticated, but sometimes not sophisticated is good. Now, weighted round robin. So in this case, what if web server 1 was less powerful than web server 2? So in this case, connection 1 might go to web server 2, connection 2 go to web server 2, then connection 3 go to web server 1, and then back to connection to web server 2 again. So just by knowing that one web server has higher performance than the other, we can weight it. We can send more incoming connections to one web server rather than the other. once again, this is one of those technologies where the load balancer doesn't know much at all about the web servers, and it makes for a very uncomplicated, very basic scenario. Dynamic least connections. All right, so here we've got number of active HTTP connections. Now, what this gets at is this idea that our incoming connections are not just one shots and done. You may have ongoing connections between the client and the web server that they're interacting with. And when that's the case, you want to maintain those connections between the client and the same web server that it started to connect with, and let that turn into an ongoing connection. Now, this is a good technology, but there's other ways to approach this. One of those other ways to approach this is through the use of cookies, so that when your client request comes in, it brings in more than a GET request for index.html. It brings in a GET request, and then it brings in a cookie that's got the history of your involvement with this website. The web server then updates that history of your involvement with the website, and gets you index.html or whatever it is you're requesting, and then sends all of that information back to the client, back to the person who's requesting this. Your client then updates the request again and sends the request for image1.html or whatever the next page is that you request, plus the updated cookie. Now, by having that updated cookie go back and forth all the time, what that does is that allows the web server to use HTTP, which is a stateless protocol, in basically a stateful fashion. Now, state doesn't really reside at the web server. It really is stateless. But the state is passed back and forth in the cookie in a way that makes it so that it appears as though you've got a stateful set of transactions happening between your browser and the web server that you're interacting with. That way you don't have to log in every time you request something. It keeps track of your browsing history. There's a lot of stuff that happens in those cookies, and that's what makes us able to use the stateless protocol in this kind of a stateful fashion. Dynamic fastest, we can now so this one, this least connection, let's see, least connection, the load balancer doesn't really need to know what's going on the web servers, but here it does. And in this case, or the load balancer keeps track of this time to response, but I think it would want to know what was going on those web servers. Now, that's important because if you look at our kind of random load balancing techniques, or first one, then the other, then the one, then the other, those kind of things are nice because there's no need for the load balancer to have any real processing power to keep track of the state of the web servers that it's interacting with. But with this protocol, it does. It needs to know what's going on board those web servers, so that there's a return set of traffic that comes from the web servers back to the load balancer. And the load balancer's now got to maintain a table that says what's going on those individual web servers. That's very different from those very basic protocols that we looked at before. And anytime you add more processing, you add more opportunities for mistakes to be made. And so, is this the best? I don't know. it depends on the particular workload on your particular application. But this is clearly more complex than the other technologies that we've looked at before. Now, do we only have load balancing across web servers? No. We could easily have this kind of a multi-master database service that's going on our Galera cluster, whatever that is. Now, most of the time when you have multiple database servers out there, or you need multiple database servers, what you'll do is you'll have one of those database servers be the master and the other database servers be replicas of the master, and they would periodically update themselves. And the way that you would organize that is that you would say that, well, a huge percentage of our traffic coming into our web servers is just browsing traffic. So that browsing traffic we're not going to send to our master database server. We're going to send the browsing traffic to our replica servers. And then when a user actually goes to buy something, then we'll transfer their connection from the replica servers to the master server. And then at that point, the master server will know the real information because it's our single source of truth. That's what database servers are. But here's a multi-master database service, and that's kind of interesting. Now, do we ever interact with multi-master database servers? The answer is an emphatic yes. The Active Directory is a multi-master database service, and of course we use that all the time. But most of the time we're going to have a single master and multiple replicas. And you've interacted with this. Anytime you are on an e-commerce site and it tells you the inventory level, and it says delivery in 1 day, in 3 days, and you think, oh great, because that's when I need it. I'm going to buy it right now. And then you click on the buy button, and then it comes up and says delivery in 2 weeks. And you're like, wait a second, what happened there? You were looking at the guesstimate of inventory levels that existed on the replica database servers. Now that you said you wanted to buy it, they transferred your connection to the master database, and the master is the only one that has the real inventory levels. And the real inventory level is you're going to have to wait a couple of weeks. So yeah, we've all experienced this, but so this is another form of load balancing where we see it buried back further into the architecture. And then here's our kind of generalized picture of load balancing in a web application. So we can't have load balancers that are single points of failure. So we can't do that. So we're probably going to have multiple load balancers in there, and each one of those load balancers may have a failover load balancer that's kind of waiting in the wings for to take over if it needs to. Now we may, if we've got our Galera cluster again, where we've got our multi-master database, and here we've got our load balancer again, but we've got a failover load balancer waiting again. Now let's look at the DNS load balancing out in the front there. So the question becomes, how do you determine which load balancer an incoming connection should connect to? And the answer to that is through DNS. DNS has a load balancing algorithm built into it that allows you to return different IP addresses for different requests over time. So here we've got our example.rit.edu, and from our first user on top there, and it requests example.rit.edu, and the response gets returned 10.0.0.1. Well, the next user requests the same thing, example.rit.edu, and it gets returned 10.0.0.2. Why is that? Well, because that's DNS, balancing the load across the load balancers. This gets complicated. And yet, like I said, it's a fundamental technology that we can't get by without, because we can't build distributed architectures that make any real sense without load balancing built into this. We can't have single points of failure. We can't have load balancers that we can't have single load balancers. We've got to have multiple load balancers. We've got to have failovers built into this. It gets complicated. So I hope this was interesting to you, and I will talk to you soon. Take care. Bye-bye.